Welcome. This is a short presentation entitled The Swiss Army Knife for Test Design. I'm your presenter, Robert Sabre. I'm a practitioner in software engineering and big advocate of test design. And I like to encourage everybody on the software engineering team to be expert in many different methods of test design, especially people who have a primary responsibility in the area of testing. Test design approaches that I'm going to share with you are independent of life cycle and independent of phase or level of testing. So I'd like to share with you methods also that have all been very handy to me and to many of my peers in our first-person experience in testing. When I say Swiss Army knife, of course, this is a metaphor. A Swiss Army knife is a knife which has many different blades, and the different blades are suitable for different purposes. So, for example, if you look at this snapshot here, you'll see some of the blades look like regular knife blades. Some look like bottle openers. Some look like corkscrews for opening your wine. Some are scissors. Some are little pairs of pliers. Some are saws. And what a camper would do if they have a Swiss Army knife is they would choose the blade suitable for their purposes. And I like to suggest that as a software engineering practitioner, that you too should have a Swiss Army knife of test design approaches, and you can choose a test design approach that's suitable given the circumstances, given the problem. Is it a time to use a knife? Is it time to use a saw? Is it time to open a bottle of wine? So different blades for different purposes, different test design approaches for different purposes. When we're designing tests in a software project, we're usually designing tests to help people answer questions about the quality of a product that we're studying. So we're studying a product, we want to understand about quality. So before you start designing a test, it's very important for you to understand on your project, in your team, what is quality. Now, nobody really cares what Rob Sabre says quality is, and no one probably cares too much about what you say quality is. But your stakeholders, your product owner, your customers, that's the view of quality that matters. If you look at this picture here, you'll see it's a snapshot of a blue screen, which was what happened when systems used to crash. You get these blue screens. Some people call it the blue screen of death. But if you look very carefully and I say, what's the problem with this picture? You'll see that actually the problem is there's a bug in the image file, and the JPEG is actually twisted. You'll see about a quarter way down the page, it's twisted. So I've got a twisted JPEG picture of a blue screen. What is quality? There's many different views. Among my customers, I've collected at least 15 different views of quality. It's important for you to understand what view matters, and this will bias how you want to design tests and what matters for you. So Phil Crosby would have argued that quality is conformance to requirements. A lot of people care about that. And if that's true, then we have to know what's required, how we prioritize requirements, what matters. Some people would say, as Jerry Weinberg, that quality is value to stakeholders. Well, different stakeholders value different things. So who are the stakeholders and what do they value? And by the way, these values vary with time. So if you're going to be designing tests and quality is value to stakeholders, it's very important to know who are the stakeholders and what do they care about at the time you need to design your test. And perhaps one of the most important views of quality is from Joseph Juran's perspective, where he says quality is not conformance to requirements, but quality is suitability to purpose. Can the customer, can the user do something useful with the software? So before designing test cases, it's very important to know what is quality. And we're going to be studying the software, testing the software to answer questions about quality. So it's important to know what is quality, what are we looking for. There's certain issues that are really critical to test design, and they have to do with the nature of software testing. And the nature of software testing is expounded quite clearly by the work of Edgar Dijkstra in the 1960s, when he basically studied applied discrete mathematics to software engineering at the time. He was a pioneer in that area, solved many cool problems like the traveling salesman problem, invented modern structured programming, and studied testing. And this is Dijkstra's principle related to testing. He says program testing can be used to show the presence of bugs, but never to show their absence. No amount of software testing can demonstrate that a piece of software is bug-free. Therefore, we know that testing is intractable. Even the simplest feature has an infinite number of possible test cases. So there's an infinite number of possible test cases. Testing is intractable. Complete testing is impossible. You will never be able to test everything. Complete testing is impossible. And lastly, there's always another test idea. The beautiful thing about Dijkstra's principle is that testing, because testing is intractable, there's always another way. There's always another approach. There's always another test idea. So there's always another way to think of things. There's a lot of different ways to design tests for the same feature, the same part of the application, the same functionality, the same workflow. It's important when we're designing tests to understand context. Contexts are factors that influence the project. Factors related to the business, factors related to the technology, factors related to the organization, and factors related to cultural elements of the system. And as these factors vary, so too does what quality concerns we have are, so too does our test design vary. So it's very important to understand on any given project before you start designing tests, what are the business, technical, organizational, and cultural factors that surround the project. So you need to have a lot of this background before getting into testing. Test design also may vary a little bit depending on your SDLC. Now, SDLC stands for Software Development Lifecycle, and in different life cycles, we have different times we do different types of testing, different focuses of testing. We could have waterfall models, which are phased, structured models, which have established clear workflows, and iterative incremental models, which are a little bit more aligned to stuff today. You might see agile stuff like Scrum and Kanban. So different life cycle models would necessitate different types of testing at different times. And then it's very important for us to also understand the workflow of software engineering. For example, how do we organize and prioritize requirements? How do I know one requirement is more important than another? How do I organize and prioritize my code? What is my source control system? How am I associating code to requirements? How am I associating the tasks to the code to the requirements? And the tracing and the management of all these things. It's very important we understand how that is and the relationship between the code and the features. And then there's the prioritization and organization of tests and bugs. It's important for us to have the workflows established before we start designing a test. So we should be aware of the SDLC and the workflow before we start designing tests. The exact same feature may come up with a very different test design depending on lifecycle requirements, workflows, and prioritization strategies. It's important for a team to understand what it means for a feature to be done. When we're looking at designing tests, we're trying to answer the question, are we there yet? Are we done? So done matters. In Agile teams, you'll see people say done means done. No more analysis, no more design, no more coding, no more testing, no more refactoring, no more integration. Everything's been demonstrated. The product is shippable. In your case, what does done mean? We should design tests to help us answer the question, are we there yet? Are we done? Can people use our code? Can we ship our code? It's important for us to understand the depth of our testing, the scope of our testing. For example, scoping software testing is often a question of looking at it. What part are we looking at? What are we going to focus on? What features matters? What features don't matter? We can look at the environment when we're scoping testing. What platforms matter? We can look at data. What type of data matters? We could look at non-functional attributes of a system or characteristics of the system. What characteristics matter? And we can look at notions of completeness or coverage. What coverage matters? Do we have to make sure all the requirements have been executed? Do we have to make sure all the scenarios have been executed? Do we have to make sure all the workflows have been executed? So this is very important to know the scope of our testing. And for any test objectives, it's also important before you start to say, hey, wait a sec, how deep are we going to go? Remember, testing is intractable. We can keep testing forever. How far are we going to go? And for each testing objective, I suggest that we should have an idea before we start. Are we going to test at light, shallow, deep, or harsh? And I urge teams to deliberately choose a depth of testing, but to keep in mind that as we test, we learn more and more, and the more we learn, the better idea we have about what's a relevant depth of testing. So the depth of testing and the scope of testing should probably be varied as we learn while we're testing. So that's before we start designing tests. Now, let's take a look at the elements of the blades of our testing. So the first blade I like to look at is called variable mapping. So this is a blade in my Swiss Army knife, and I like to start with this one. It's hard for me to imagine a project that wouldn't benefit from this blade once in a while. Variable mapping, test design approach. To vary is to change. Software behavior depends on the values of many variables. Anything with influences the behavior of software could be a variable. And what we should be doing is, when we're looking at a feature or an objective of our testing, we should look at the basis. What information do we have? Try to identify variables that influence the behavior or that are outcomes of the behavior. And we should stick our nose everywhere looking for it. There's a lot of potential sources: conditions, environments, rules, constraints, action states, and tons of other things. So we try to stick our nose everywhere looking for variables. Variables are not just things written down in the requirements. Variables are things which can change, which influence or are influenced by the behavior of the software. And I like to create a mind map of my variables. Mind maps are things that I was first introduced to by Tony Busan's work in the area. He wrote a beautiful book called the Mind Map Book. Mind maps are just visualizations where you have basically objects which are nodes or pictures and lines which are relationships between them. And we can visualize a lot of information about our variables by creating mind maps of them. So a couple of examples. Imagine you're testing Gmail and you want to test to make sure we can send emails with image attachments. So we could create a variable mind map of that. We can try to study Gmail, watch people use it, look at the requirements, look at the online resources, documentation, and maybe we'll have variables related to the environment, resources, software connections, maybe related to how you log into Gmail, maybe related to the state of the inbox for Gmail, maybe related to the state of the email at the time we're sending the attachment. So these are all different types of variables that influence or are influenced by the behavior of the system under test. Related, of course, to the scope of our testing. So this is a sort of broader picture of Gmail variables. So the map is a visualization of them. And what's really cool, and this is an example from an insurance company where we have variables related to a feature related to counseling policies. So all of them basically mapped out. And we get these by looking at requirement documents, design documents, talking to people, talking to customers. So this big visualization of the variables. And once we've got the visualization of the variable, then the first real test decision we make is, how do we act on the variables? And the beautiful thing here is there's only 4 ways we can act on a variable. The first thing is, maybe we can ignore a variable. In my view, it's more important to ignore something on purpose than it is to skip it because you didn't think of it. Sometimes we're going to put default specific values. So we're not going to change the value, but we're going to put it as a control thing. For example, we might use a standard hardware, a standard software, a standard operating system, a standard browser version, we're not going to change it. We can put specific values where we'll use other test design approaches to identify specific values, and we can also observe a value, not just control it. So those are the 4 things we can do with a variable. So for every variable we identify, we figure, do we ignore it, default it, choose specific values, or observe it? So those are the 4 things. So once we have chosen a variable and we are going to deliberately choose values for it, a great way to choose values is called variable partitioning. I like to use variable partitioning using equivalence classes. This is a term that comes from domain testing. An equivalence class is a subset of all the possible test values a variable can have. And this subset has certain properties. Each member of it would provide the same info if we tested it. Not the same result, but the same knowledge. Each variable can have many classes. They're not mutually exclusive. They really help focus testing by letting us reduce the number of test cases to learn the same amount of stuff about the application. Some people learn about these partitions using Venn diagrams. Venn diagrams is a fantastic way to represent the partitioning. However, it is very hard to edit and manage. So what I tend to do is use mind maps. And the type of mind maps I create break down one variable into 3 types of classes. One is based on application logic. So what are the business rules? One is based on input. How did the data get there? And one is based on memory. How is it stored in program memory or a database schema or otherwise any other processing? So I call this the AIM partitioning. AIM is just an acronym to help me remember this. Application logic, input method, and memory. If you take a look at a simple example, say you have a web application that computes a square root. Well, you might talk to a mathematician who specializes in numeric calculations to help you identify the A classes. So this is based on the application logic. So in that case, they might say, well, there's 3 classes. It's greater than 0, less than 0, or equal to 0. And if it's greater than 0, it can be a whole number or a number with a fractional part. And if it's a whole number, well, it could be a perfect square, prime, or something else. So the end nodes of this map give you the classes. Then how data gets there? Well, it could be numeric or non-numeric. If it's numeric, it could be in a supported or non-supported syntax. And if it's non-numeric, it could be alphabetic, control characters, or binary large objects. And if it is alphabetic, it could come from all sorts of different languages. So we basically have a whole bunch of non-numeric classes. And then for the M classes, well, it's not too tricky. We talk to the programmer, we look at the variables they use, and we say, well, there's at least 3 classes, some values that are too big to fit in, some values that are too small to fit in, some values that are just right to fit in. So the end node of the mind map here will become partitions, and basically then you need to test a small sample of values from each partition. I like to choose randomly 3 values from each partition. There's a work through example here of the Gmail 2 composed. If you're interested, contact me. I'll be glad to send you tons of examples of fully worked out partitions. So here's some information about the 2 composed, which comes from Gmail documentation. And there's a breakdown of the map. You can study this offline, but the application logic has a lot to do with the name and domain and how they've been assigned. The input classes has to do with the syntax of the email address, and the memory classes has to do with the length of the string and the contents of the string. And this breaks down to, if you want to look at them a little more detailed, there we go. So, variable identification, Blade I use all the time. Partitioning, Blade I use all the time. What about boundaries? Partition boundaries. Pretty much 80% of the people I run into in testing are already using this Blade, although they usually don't really have a very rigorous definition of it. So what I want to say is anytime we test a class or a partition which has a continuous range of values, the boundary tests would be around the extremes. So it's important to test the lower and upper boundaries, right on the boundary, a little below, a little above, and any other edge conditions that you might identify. So those are boundary tests, and a lot of bugs live around boundaries. Diving from the subject of boundary tests to another blade, multi-variable blades, perhaps, this test design technique called usage scenarios. Ask not what your feature does for a user, but ask what your user does with the feature. We take a look and we're modeling usage of it. We take a look at real usage for each type of users. Maybe we have an analysis that's done that. Maybe we've created storyboards that done that. Every single scenario can and almost always does touch many, many functions. So this is broadly cross-functional testing. Take a look, for example, at mapping out who are the users and what do they do. So what I like to start with scenarios is to identify who are all the different users of the system, and then what is the typical work that they do. I like to storyboard to identify scenarios. So for example, buying a book, you conceptualize, hey, I want to buy a book. You go to Amazon, you choose it, you through the search mechanism, you select it, put it in the shopping cart, then you give your credentials and log in to buy the book, and then at the end it gets actually delivered to you. So this is a step-by-step storyboarding. Now storyboarding, usually each step is broken by a point where a user enters data or makes a decision. When we create tests based on the storyboard, we basically parameterize the experience. That means that anywhere where the user enters data or adds or makes a decision, we turn that into a variable. And when we test it, we walk through it from beginning to end, always through it in beginning to end in the natural order from the storyboard, but using pre-selected input for each time we walk through it. And we also try to run each test as if it were an independent user experience. So that's storyboarding, test design technique. There's control flow, which is a test design technique, which is very handy when we have workflows, data flows, process flows, code flows, transaction flows. Anytime we have a network of features that we have different pathways through it, this is a fantastic test design technique. The basic approach, create a control flow diagram, and then we find what are called the basis paths. So the basis paths is the minimal set of transactions where we execute every step at least once and every decision, every way it can go at least once. Now, control flow diagrams, anybody can be taught to create these. You can interview people to learn about them, but basically the idea is there's circles and lines. The circles represent process steps. So here A flows to B and B flows to C. So the arrows represent the flow between process steps. There's loops. So A flows to B, B flows to C flows back to A. That's a loop. There's decisions. A flows to B or A flows to C. There's junctions. C comes from A or C comes from B. We have this beautiful equation called McCabe's cyclomatic complexity, which tells us how many basis paths there are in this network. A basis path is the minimum number of paths which exercise every step at least once, and every decision, every way can go at least once. And also you can combine the basis paths to create any path through the system. So the equation P equals E minus N plus 2. E is the number of edges. N is the number of nodes. The circles are the nodes. The lines are the edges. So P is the number of paths. So in this case, there's 3 basis paths. There's an algorithm, which is well understood, published in Lee Copeland's book, A Practitioner's Guide to Test Design. And this method of finding the basis paths means you find a typical one to start with. That's the first path. Then to find the second path, well, you go through the first one, but flip your first decision, keep the rest as similar as possible to the original. Then you keep going down, flipping decisions on the first one until you've exhausted them all. Then you pop it off and go to the second one and continue until you run out of paths, until you've exhausted all the paths. Tedious, by the way, to follow that algorithm, so it's a good idea to try to use a tool. There's an insurance control flow diagram project here I worked on. It was a system which had basically 60, if I'm not mistaken, 60 possible screens to get to. And They basically can execute every screen in every order at least once. And so basically the idea was they wanted to test all, the pathways between the system to try and find bugs related to the order of operations. When doing the math, it worked out that there would have been 60 factorial possible cases in all, which is 8.32 times 10 to the 81. And unfortunately, that's a bit too many test cases. In fact, if you take a look at NASA's work with Hubble, they estimate there are between 10 to the 79 and 10 to the 82 atoms in the visible universe. And the implication here is that my customer had a desire to do more test cases than the number of atoms in the visible universe. So rather than doing that, we investigated and found out that there was workflow models of the system. So rather than testing all the combinatorics and all the permutations, we said, let's try looking at the workflows and do a control flow analysis. So I built this by hand, control flow diagram, and I found out with McCabe's equation that there were 26 basis paths or 22 basis paths, and this is 22, and this applying the algorithm by hand is the result. And what we did was for each of these 22 tests, we created the data and the transactions, walked through every one from beginning to end, and were able to find and fix relevant control flow bugs. And after the pilot testing, they were able to actually release into production with no other software engineering changes. There's other types of blades for multivariable systems. So we had usage scenarios, we had control flow diagrams. There's also decision tables. So decision tables take place when we have complex business rules. If you take a look at this beautiful example from the FAFSA Federal Student Aid Form, you'll see that just reading some of this gibberty-goop, if your parents are both living and married to each other, answer the questions about them. If your parents is widowed or single, answer the question about that parent. If your widowed parent is remarried as of today, answer the question, dot, 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 dot. All of this gibberty-goop. If you have systems and requirements that sound like that gibberty-goop, maybe it's worthwhile to use a decision table. They're handy for application logic, business rules, regulations, any system that has multiple conditions and multiple actions. So the method of test design around decision tables is to identify what are the conditions, what are the actions, relate conditions and actions, which things are called rules, and then use logical reduction to try to represent the relationship between conditions and actions in the minimum number of rules you can. And then for each rule you've got, create a test case to exercise each rule. So if you take a look, this is usually done in a table. You can put this together with an Excel spreadsheet. A few rows are tied up for conditions, a few rows are tied up for actions, and a bunch of columns are tied up for rules. Building an example. So this is for a university acceptance application. The conditions are your standardized score, academic prerequisites, and where you live. And the possible actions are, we accept your application, we redirect you to a different program, we give you a conditional acceptance, we reject you outright, or we offer you a grant. And you'll see that the table is filled in and reduced. So if we take a look at it, let's read rule number 14. It says, if you have a medium SAT score and you only have the core prerequisite, but you live in the state, then we're going to give you a conditional acceptance, and we're going to offer you a grant. So you see it's read linearly top down. And so for each and every column here, you would create a test case. So that's the decision tables. There's another type of model we use if we have a stateful system called state models. A stateful system is interesting. A state is a situation which can be recognized if it occurs again. So if you have a system which is stateful, then you can take a look at it and say, if it's stateful, maybe I can test this by using state transition diagrams. Transaction systems, embedded systems, process flows, workflows, user interface systems are examples of stateful systems. There's also today REST APIs, which are stateful systems as well. State models have basically very few elements. Circles represent states, arrows represent transitions between states. The idea for state modeling, identify what are the states, what are the transitions, then identify what triggers a transition and if there's any variable outcome for a transition, and then come up with tests that get to every state. So at least one test to get to every state, at least one test to exercise each transition, at least one test to cover different pathways through the state model. And you can also consider tests which try to trigger transitions that are not supposed to happen. We have an example from the insurance industry where you have a policy starts in a null state, then it gets submitted into a request state, then we check the credit, it becomes approved, then we make a policy, it becomes issued, then we get the first payment, it's paid, and then it's active. And if someone is late in payment, well, we have sort of states of it to be in basically a situation where we're going to collect later, or there's all sorts of ways where if they never pay, it gets canceled. Then you have combinations test design techniques, and this is the blades that come up often in my testing. One is called Pareto combination testing. The Italian economist Vilfredo Pareto, he identified that 80% of the money is in the hands of 20% of the people. Joseph Juran applied this to engineering and came up with the 80-20 rule, which means that there are a vital few and a trivial many. 20% of the population accounts for 80% of the measures. In a transactional system, what you would do is you'd look at a transaction history from your system or from similar systems, put it into a histogram, and try to identify the sweet spot and build tests to exercise the 20% that are more frequent. So this is an example of what the histogram looks like. So this is a histogram with about 250 columns. So the 50 bottom here, about this part, that's your sweet spot. So what you want to do is take those 20% and test those. Now, you're not testing everything. What you demonstrate with the Pareto analysis is that normal things work normally with normal data. Normal people can do normal things normally. Outliers may not work, but this is something that we can't test everything. So we use Pareto analysis to find a realistic subset. And we focus on testing what real people really do most of the time. If there's outliers not working, well, we're going to have to do some sort of patch later on to fix that. Then there's pairwise combinations testing, which is sort of the opposite of Pareto combinations testing. In pairwise combinations testing approaches, we take a look at subsets of possible combinations which exercise thoroughly the relationship between different variables in the system. So we try to start by identifying what are dependent variables of interest. So we get a bunch of variables. Then for each variable, you choose the values that are interesting, maybe by partitioning. And then for each pair of variables, you define at least one test which exercises all possible combinations. So for example, there's tools to help us do this, by the way. All pairs are picked, available, all free, beautiful tools. Here's an example. Let's say we have a chocolate wrapping device, and we've identified these 10 variables: chocolate type, configuration, paper, ribbon, conveyor speed, box type, viscosity, box size, weight, and size. If I wanted a pairwise complete set, so I would use a tool like picked, give it this input, and then see what the outcome is. Now, if you look at the outcome here, you'll see, well, there's a whole bunch of variables, but I have a test case here in this list. Every chocolate with every configuration at least once. Every chocolate with every paper at least once. Every chocolate with every ribbon at least once, ... Every chocolate with every size at least once, plus over and above that, every config with every paper at least once, every config with every ribbon at least once, ... Every config with every size at least once, all the way to every weight with every size at least once. Any two variable, every combination at least once. And that can be done with a grand total of 51 test cases. Now, if I did every combination of all of the variables, it would take me over 2 million test cases. So this subset of them is considered a very strong subset, and it's very good at bubbling up bugs which relate to multiple factors interfering with each other. Sometimes you have a testing situation where you have to put constraints in. So constraints are limits so that you will not generate impossible combinations. For example, for the chocolate wrapping thing, it's impossible to wrap a hollow chocolate with wire. It's impossible to put a ribbon if there's no paper. So we can put those constraints, and by having those constraints in, the tools will basically generate a set of tests which have pairwise completeness and do not violate the constraints, in this case, getting up to 55 test cases, which is still dramatically less than a couple of million test cases. So that's a bunch of examples of test designs from my Swiss Army knife. There's many, many more. And of course, to gain proficiency in this, you'd have to more thoroughly go through each technique and watch lots of examples and try it out yourself. And you have a very good day. It's been fun talking to you. Until next time.